Welcome back. Today we're going to talk about analyzing graphs of functions. This is section 2.3. If we're going to analyze a graph of a function, we really need to know what a graph of a function is. A graph of a function is traditionally, we see that line or that curve or maybe a collection of lines on a coordinate plane. But a graph of a function is a collection of points. If we were able to zoom in on a curve infinitely, infinite zoom, we'd keep going and keep going and keep going. We'd see a collection of points. And really, the smoothness of the curve comes from the fact that the points are so close together because there's so many of them. And really, they look like this. It's f of x as the y, and the x is what we put in. So the x is that independent variable, and the f of x is that dependent variable, that y is that dependent variable. Okay? And so, if we're looking at a function of a graph, I want to just look at this for just a second. If I took this collection of buildings, this skyline, and I just kind of drew a curve that sort of had the tops of these buildings and kind of took it into account, those sorts of things, I want you to think about this. Along the bottom here, and I'm going to try to show you using this green line, like let's say this was the x-axis, and then up this way was the y-axis. What happens is, at every single point along the graph here, and there's an infinite number of them, there's infinitely many of them, any of these possible points here along this x-axis, x describes the distance from x equals 0. Okay, and so that's the distance x. But this height here, the tallness of the building, is my y, but it's equal to f of x. The height of any given point on the graph is the height that's defined by the function of x. And so if it's below the x-axis, that would be still a distance from this y equals 0 down here. And so each of these points has a height, if it were going to be drawn as a rectangle, of f of x. And that's just kind of another way to think about it. As we move on here to this next. All right, so as we look at this example 1, we're going to be using the graph of the function to find the domain of f, the function values of f of -1 and f of 2, and also the range of f. Well, let's look at the domain of f first and what that means. The domain of f is the x values. And so that's the input value. So if I'm looking at this graph, I'm taking this at face value. What is on this graph currently? And so as we look here, we see that the scale goes by 2s, and so there's 4 blocks in 1 until we get to a big gray. So that's 2 there. And so as we consider the domain, I've got to figure out how far it goes. Well, it goes from here to here. Well, what does that mean? So I obviously have, 2 here, 4, and then this one goes another 1. So this is 2, 2, and 1, and then it's another 1 this way. And so what's my domain? Well, my domain is a total of 6 numbers. Well, that doesn't tell me domain, because domain is going to be what are the x values. I just need to figure out exactly what's going on. And so my domain goes from -1 to 5. And is it open or closed? Well, as you can see, this closed dot here tells me that -1 is included, but this open dot over here tells me that 5 is not included. Okay, and so that's going to be a case where it's not closed, and so it's not included. The function values of f of -1. Well, f of -1 means that I'm looking at where the function, what it's equal to at -1. And I'm doing a little erasing here to make it clearer to see. And so as we consider f of -1, I need to go to -1, which is right here, and I need to look at where it actually is. Well, it's this would be 1 here, and so this would be 1.5. So at f of -1, my value is going to be this point right here, which is at 1.5, okay, because it's almost 2. All right, my range of values. This is going to be my y stuff, my y values, like how much, how high can I go, how low can I go. And so my range is defined by my upper and my lower, and we'll notice that up here it's at 3, so 3 is my upper. And my lower is going to be down here at -3. And to determine whether they're open or closed, I look at my dots. My dots are both closed, and so I have a range of -3 to 3. And that's exactly how that works. You look at the graph to determine is it open or closed, what are the values, and I can look at my graph and see. I just realized I never did determine f of 2. Let's look at f of 2. If I go over here to 2, this is going to be my x, so when I go down here, I'm going to be at, well, here's -1 and here's -1.5, so we're about -1.25 on that one. So I'm going to my graph and looking to see where those points cross. Okay, that's how you use a graph to determine. We're analyzing that. Let's look at the next one, the vertical line test. Now, the vertical line test tests to see if it's a function. A graph is a function. And that means that it maps 1x to, or 1x maps to 1y and not 2. So here, any of these points along this bottom line, 1x would go to a y. And if I went to that same x, it would go to y again. So this is a function. Not a function would mean x would go to a y, but then x would go to a different y. So it would be a y1 and a y2 situation. That's why this one does not pass the vertical line test, because for this x right here, it's got 1, 2, 3 values here. And as we look at that, that means that this single x maps to 1, 2, 3 values. And so the vertical line test tells us if it's a function, because it tells us, well, how many y values am I getting for any one x? Here, if I drew any vertical line, that would mean that any of these x's that I'm coordinating with only have one value that they correspond to in my y coordinate plane. Up here I've got 1, 2, 3 values, which is a problem. Okay, so the vertical line test, if you can put your pencil down on that problem or on that graph, and you can see that if it's perfectly vertical, it touches 2 points, then it's not a function. Let's talk about finding the zeros of a function. So that's where f of x is equal to 0. So as I do this, really what I'm saying is, where is it equal to 0? And so these are going to be problems that we've kind of looked at before. So 3x squared plus x minus 0. Now we can solve these any way possible. And so in this case, I'm going to factor it. And so if I factor it, I'm looking for two things that are going to multiply to -10, but add to 1. And so I've got to take into consideration this 3 as my coefficient here. And so I'll know it's going to be a 3x situation and an x. And this is going to factor to -5 and plus 2. And still equal to 0. So as I solve it, I've got 3x minus 5 equals 0, and x plus 2 equals 0. Add 5 to both sides. 3x equals 5. Divide by 3, and so x is equal to 5/3. So that's one of my x's where it's going to be equal to 0. Subtract 2 from both sides of this one, x is equal to -2. That's my other 0 there. So those are my zeros where f of x is equal to 0. In this next one, I'm going to set 0 equal to my function, 10 minus x squared. And as I square both sides, so I'll square both sides, 0 squared is still just 0, so then I have 10 minus x squared is going to be my next equation that I'm looking at. And so if I add x squared to both sides, I've got x squared is equal to 10. And as I take my square roots, I need to take into account that I have a plus or minus situation here, because I am choosing to do that. It wasn't written into the problem. So those are my x equals 0. My f of x is equal to 0. Okay. Next one, I have my h of t is this part over here, and so as I set it equal to 0, what I can do is I can multiply each side by t plus 5. And we know that 0 times t plus 5 is going to be 0 still. And so over here I've got 2t minus 3. And I'm just going to solve. These types of equations are ones that we have looked at extensively so far. And so using those strategies is going to be crucial in this case. Okay, so t is equal to 3 over 2. And so these are going to be the zeros of a function where f of x is equal to 0. So I literally set my f of x or g of x or h of t. Any of that with the parentheses, that notation, is going to be equal to 0. And this is what we've been doing all along to set functions equal to 0. Okay? Now, next one is increasing and decreasing. This is not a situation where we should be stressed out, because really I'm just drawing in a function here to show you. Decreasing, increasing. What we're looking at is, what is the general trend? So what I'm looking at is I'm looking at a function in terms of pieces, and these points right here are going to help me sort of define what's going on in a given section of a function. So like over here, if I were on the second example over here, I'm going to kind of divide it into pieces, like here's piece number 1, here's piece number 2, here's piece number 3. Okay, and so the increasing, decreasing, and constant functions, yeah, this goes up into infinity over here, this goes down into infinity, so we have to look at kind of local, like what's going on in a general area. And so as I look at this over here, this part here, this first leg of this graph, is decreasing. And so that is going to be going down and to the right. This middle part here is staying constant. It's at a level of 1 the whole time. Now, to say that this graph was constant over the whole thing would be false, because we can see that it's kind of going up on the ends. But over this interval here, it is constant. And here it would be increasing. And so we have to look at functions in terms of the pieces that they have, or where are my maximums and things like that, which is what we'll talk about in the next slide. But like part number 1 here is looking like it's going down, but it's really not going down, because we need to look at as we move to the right. Okay, so as we move to the right, so really, yes, this does continue down, but as I move this way, what is it doing? Well, it's generally increasing. Think about it as I go to the right in terms of time or whatever, it's going up. So this is an increasing interval. Number 2, as I move, again, to the right, it's generally going down. Okay, so this would be a decreasing interval. And so number 3, as it goes to the right, is going to be increasing in its what y is equal to. So yeah, it was down here, but it's increasing as it goes up. And the way that we notate this is I would have to know these points here. And what I would say is, like, let's say this was 2 comma negative 4. And this was negative 2 comma 4 up here, if I was labeling these points. What I would say is, the function is increasing over negative infinity to negative 2. Okay? It's decreasing from negative 2 to positive 2. And it's increasing over the interval 2 to infinity. Okay? And so those are that would be the way that we note that to tell us what is the interval that it's increasing over, because in general it does continue to go up, but it is decreasing over a certain interval. relative maximum and relative minimum. Once again, looking at cases where it's not the maximum of the function necessarily, but in a given area, it's a relative max. Okay, so that we use this for, you know, like we looked at a graph of the stock market, the highs and lows day to day, or the high and low for the month wouldn't be the high and low over time, but where are the highs and lows of the month? Because obviously this continues to go up, and so the maximum could be up here, which would be the overall maximum, but a relative maximum is somewhere where we see this little spike. You see how it's just a little spike there, or a little spike there. So obviously D is lower than B, but it's a relative max and a relative minimum, meaning it's the highest point in a given area, or a minimum would be the lowest point in a given area. So not necessarily the absolute minimum here, which means that's the low point of the graph, but these relative minimums mean that it's lower as it's the bottom of a valley. Okay, so it continues to go up when it comes out of that valley. Okay. Last thing is even and odd functions. So even functions look like this. If f of negative x is equal to f of x, then it's even. Here is an example. If I have h of x is equal to x squared plus 1. What I'm going to do is I'm going to do h of negative x and see what happens. So that would be negative x squared plus 1, which would mean I have the same as x squared plus 1. And because my original and my now function evaluated at h of negative x are the same, that would be an even function. Okay, so anytime it ends up the same function as the original, it's going to be an even function. An odd function would look like this. F of negative x is equal to negative f of x. Slight distinction there, but when we look at x to the third minus x, we're getting a good situation here where we can model this. And so this is actually h of x equals. So if I'm going to evaluate h of negative x, watch what happens. I'll put in negative x into my function, third minus, and then minus x. So what happens is I get negative x to the third, because it's going to be x times x times x, and then negative 1 times negative 1 times negative 1, and then plus x. And what I can do is I can factor out, and this is the tricky part, I factor it out of each one. So I have x to the third plus a negative x would just be a minus x. And if I look at this, it's my original function inside. But on the outside, I've got that negative, which is where the difference in the even and the odd functions comes. So if you evaluate it and you get a situation where you can factor out that negative from the original function, so this is the original, and I've got a negative 1 times my original function, that's going to mean that it's an odd function. We're looking for things like fifths and thirds and things like that. Okay? So that is the basics of analyzing graphs. Thanks for watching, and we'll see you next time.